All right, so looks like we've got quite the collection of chemistry notes and textbook excerpts here.
Yeah, someone's been busy.
Definitely. Balancing equations, stoichiometry, gas laws, even some periodic trends snuck in there. So are you prepping for like a big chemistry exam, or maybe brushing up for work, or maybe you just find this stuff fascinating?
Well, whatever the reason, we're about to dive deep and distill these complex topics into their most essential parts.
Exactly. You know, my first chemistry teacher was absolutely obsessed with balancing chemical equations.
Oh, yeah.
Like it was the most important thing in the world. What's the big deal with making sure everything's balanced? Like, what's the point?
Well, imagine you're building with Legos. You have a certain number of bricks, and you can't just magically create more. A balanced chemical equation works the same way.
Okay.
Atoms can't just appear or disappear during a reaction. What goes in must come out.
So it's like a strict accounting system for atoms.
Exactly. A balanced equation tells us the precise ingredients, the reactants, and their proportions needed to create the final product, the products.
So it's not just some like academic exercise.
No, not at all. It's crucial in fields like pharmaceuticals, where precise measurements are critical for, drug development, ensuring patient safety.
Okay, yeah, that makes a lot more sense now.
Sure.
It's not just about following rules, it's about understanding the fundamental principle of conservation of matter.
Precisely. And this understanding is crucial for stoichiometry, which allows us to calculate the exact amounts of reactants and products involved in a reaction.
And that has real-world applications too, right?
Oh, absolutely, especially in industrial processes where minimizing waste and maximizing efficiency are really important.
Right, so it's like scaling up a recipe for mass production.
Yeah.
You need to know exactly how much of each ingredient you need to avoid ending up with a warehouse full of extra ingredients or not enough product.
That's a great way to put it. And this is where the mole concept comes in handy.
Ah, yes, the mole. It's always kind of made me think it's something you'd find digging in your garden.
Well, in chemistry, a mole isn't a furry creature. It's a unit of measurement.
Right.
It helps us deal with the incredibly large numbers of atoms and molecules involved in chemical reactions. Imagine trying to count individual atoms. It'd be like trying to count all the grains of sand on a beach.
Okay, yeah. So the mole gives us a manageable way to work with these tiny particles.
Exactly. One mole is simply a specific number of entities, like atoms, molecules, or ions. Similar to how a dozen always means 12, no matter what you're counting.
Okay.
This becomes incredibly useful when we're dealing with reactions involving billions upon billions of atoms and molecules.
I see. Okay. So the mole concept makes those massive numbers a bit more digestible.
It does. Now, you mentioned something earlier about...
Oh, yeah. The source I was looking at mentioned something about moles of compounds versus moles of ions within that compound. Can you elaborate on that a bit?
Of course.
Yeah.
A compound is formed by combining different types of atoms in a specific ratio. For example, water, H2O, is a compound formed by 2 hydrogen atoms and 1 oxygen atom. When we talk about 1 mole of water, we're referring to 1 mole of water molecules. However, within that 1 mole of water molecules, we have 2 moles of hydrogen atoms and 1 mole of oxygen atoms.
Oh, so it's like a nested set of measurements.
Precisely.
Okay.
And this distinction becomes crucial when we're calculating reacting masses using stoichiometry.
Right.
We need to be clear about whether we're dealing with moles of a compound or moles of individual atoms or ions within that compound.
Got it. Okay, so we've tackled balancing equations and the mole concept. Now let's talk about gas laws, particularly Avogadro's law. What makes this law so special?
Well, Avogadro's law states that equal volumes of gases at the same temperature and pressure contain the same number of molecules.
Okay.
This seemingly simple statement has profound implications. It allows us to directly relate gas volumes to the mole ratios in a balanced equation, making calculations involving gas phase reactions much easier.
So if we know the volume of one gas involved in a reaction, we can use Avogadro's law to determine the volumes of the other gases involved.
Exactly. Let's say we're burning propane, C3H8, and oxygen, O2, to produce carbon dioxide, CO2, and water, H2O. Using the balanced equation in Avogadro's law, if we know the volume of propane we're burning, we can directly calculate the volume of oxygen needed and the volume of carbon dioxide produced. No need for complex conversions.
Wow, that's incredible. It's amazing how these, seemingly abstract concepts have such practical applications in the real world.
Absolutely.
You've got me thinking about the chemistry behind it, like everything from baking a cake to inflating a balloon.
And that's the beauty of chemistry. It's all around us.
Yeah.
Now let's shift gears a bit and explore another fundamental concept, Concentration.
Concentration.
It's a term we encounter in everyday life, even outside the lab.
Oh, for sure.
Think about making a cup of coffee.
Yeah.
If you like it strong, you add more coffee grounds to the same amount of water.
Right.
That's increasing the concentration, the amount of solute the coffee
Okay.
dissolved in a solvent, the water.
Makes sense.
And in chemistry, we use specific methods like titrations to determine the unknown concentration of a solution.
Oh, titrations. I remember those from chemistry lab.
Oh, yeah.
Like using those burettes and pipettes, carefully adding drops of one solution to another until something changed color.
Right.
I always felt a bit like a magic trick.
It's not magic, but it is a carefully controlled chemical detective game. In a titration, we use a solution of known concentration, the titrant, to determine the concentration of an unknown solution, the analyte.
Okay.
By measuring the exact volume of titrant needed to react completely with the analyte, we can use stoichiometry to calculate the analyte's concentration.
Oh, I see.
Now, you mentioned something about...
The source also mentioned something about concordant results. What does that mean?
Concordant results refer to measurements that are close together, indicating good precision and reliability. In a titration, we typically perform multiple trials and look for consistent results. If our measurements are all over the place, it suggests there might be errors in our techniques or measurements.
So it's like a quality control check for our experimental data.
Exactly.
We want to make sure our results are, consistent and reliable before we draw any conclusions.
Precisely. And this emphasis on accuracy and precision is crucial in many fields, not just chemistry.
Right.
Whether you're analyzing data in a research lab or formulating a new product, having reliable measurements is essential.
Right. We've covered a lot of ground. Balancing equations, the mole concept, gas laws, and even delved into the, intricacies of concentration and titrations. Are we missing anything important?
Well, we can't forget about limiting reactants and yield. Chemical reactions don't always go perfectly according to plan.
Right. Sometimes you run out of one ingredient before the others, like when you're baking and run out of eggs.
Yes.
The source refers to this as the limiting reactant.
Yes.
It puts a cap on how much product you can make.
Exactly. Imagine you're assembling bicycles.
Okay.
You need 2 wheels, 1 frame, 1 handlebar, and 1 seat for each bike. If you have 100 wheels, 60 frames, 50 handlebars, and 70 seats, you can only make a maximum of 50 bikes.
Right.
The frames, in this case, are your limiting reactant.
So even if you have plenty of wheels, handlebars, and seats, you're limited by the number of frames you have.
Correct. And in chemistry, the limiting reactant determines the maximum theoretical yield, the amount of product you could potentially make if everything goes perfectly.
Okay, but things don't always go perfectly, right?
Right. In the real world, reactions rarely achieve 100% yield. There could be side reactions, incomplete reactions, or losses during purification.
And that's where percentage yield comes in.
Exactly. Think of it as a measure of efficiency.
Okay.
How close did we get to the ideal outcome? This concept is critical in industrial chemistry, where optimizing yield can save resources and reduce waste, contributing to a more sustainable process.
So it's like trying to get the most cookies out of a batch of dough. You might lose some to burnt edges or crumbly bits, but you always aim for the most delicious cookies possible.
Now, are you ready to tackle the periodic table?
Let's do it.
It's not just a random arrangement of elements, it's a roadmap to understanding their properties and how they behave in chemical reactions.
It's like the ultimate cheat sheet for chemists.
Yes, it is.
The periodic table is organized by atomic number, the number of protons in an atom's nucleus,
Right.
and electron configuration, which dictates an element's chemical personality.
And the brilliance of the periodic table lies in its ability to reveal trends in properties like atomic radius, ionization energy, and electronegativity.
I remember learning about these trends, but could you refresh my memory on how they work?
Certainly. Atomic radius refers to the size of an atom. It generally decreases as you move across a period from left to right,
Okay.
and increases as you move down a groove from top to bottom. This is due to the interplay of 2 factors. The increasing positive charge of the nucleus as you add more protons,
Okay.
and the shielding effect of inner electrons.
Shielding effect. That sounds interesting.
As you move down a group, you're adding more electron shells.
Right.
These inner shells of electrons partially shield the outer electrons from the full attractive force of the nucleus.
Okay.
This shielding effect outweighs the increasing nuclear charge, leading to a larger atomic radius.
Oh, so it's like a tug of war between the attractive force of the nucleus and the repelling force of the electrons, with the shielding effect playing a role as well.
Exactly. And understanding these trends helps us predict things like reactivity, for example, ionization energy. The energy required to remove an electron from an atom generally increases across a period and decreases down a group.
Okay.
This is because as you move across a period, the increasing nuclear charge holds the electrons more tightly, making them harder to remove.
Right.
Conversely, as you move down a group, the shielding effect makes it easier to remove those outer electrons.
So elements with low ionization energy, those that lose electrons easily tend to be more reactive.
Precisely. Take sodium, for example. It's in group 1, has low ionization energy, and is highly reactive. It readily loses its outermost electron to form a positive ion, Na plus Ag, which is why it reacts so vigorously with water.
It's like sodium is like eager to get rid of that electron, making it a bit of a chemical party animal.
And this reactivity is directly related to its position on the periodic table and the trends in atomic properties.
It all starts to make sense. The periodic table is like a giant puzzle.
It is.
And understanding these trends helps us put the pieces together.
And speaking of reactivity, let's dive into some specific examples. Our sources focus on metals and nonmetals, particularly the reactions of group 1 metals, the alkali metals, with water.
Ah, yes. The classic alkali metal explosions. I remember those videos from chemistry class.
Those vivid demonstrations illustrate the increasing reactivity of alkali metals as you go down the group. Lithium, at the top of group 1, reacts gently with water, producing bubbles of hydrogen gas. Sodium reacts more vigorously, and potassium reacts even more dramatically, often igniting the hydrogen gas produced.
So the bigger the alkali metal atom, the more reactive it is with water.
Exactly. As we discussed earlier, the outermost electron in larger alkali metal atoms is further away from the nucleus and is shielded by more electron shells.
Right.
This weaker attraction makes it easier for the atom to lose that electron, resulting in a more vigorous reaction with water.
It's a dramatic demonstration of how periodic trends translate into real-world phenomena.
Now, what about the halogens? I remember them being quite reactive as well.
Yeah, they are.
The halogens, the elements in group 17, are notorious for their reactivity, especially with alkali metals.
Right.
They have 7 valence electrons and are highly electronegative, meaning they strongly attract electrons. They only need to gain 1 electron to achieve a stable octet, making them very reactive.
So it's like they're always on the lookout for that one missing electron to complete their outer shell.
Right.
And like the alkali metals, their reactivity also follows a trend within the group, right?
Precisely. Halogen reactivity decreases as you move down the group. Fluorine, at the top of group 17, is the most reactive halogen, followed by chlorine, then bromine, and lastly, iodine.
Yeah.
This hierarchy dictates the outcome of these displacement reactions.
So fluorine is the most aggressive electron grabber of the halogens, while iodine is a bit more laid back.
That's a good analogy.
Okay.
This trend in reactivity is again related to atomic size. As you go down the group, the atomic radius increases, and the outermost electron is further away from the nucleus. This weaker attraction makes a halogen less reactive.
It's amazing how the arrangement of electrons in an atom dictates its chemical behavior. It's like each element has its own personality based on its electron configuration.
And these personalities really shine through when we look at how elements form oxides.
Oxides, those compounds formed when an element reacts with oxygen. I remember learning about acidic and basic oxides, but I'm a bit fuzzy on the details.
Well, as you recall, oxides are compounds formed when an element reacts with oxygen. And just like the elements themselves, oxides exhibit a wide range of properties, from acidic to basic.
Right, and this acidity or basicity depends on the nature of the element forming the oxide.
Exactly. Metallic oxides, like those formed by group 1 and group 2 metals, tend to be basic.
Okay.
They react with water to form alkaline solutions.
Right.
Like sodium oxide reacting with water to produce sodium hydroxide, which is a strong base.
And non-metallic oxides, like those formed by elements in groups 14 to 17, tend to be acidic. They react with water to form acidic solutions, like sulfur trioxide reacting with water to produce sulfuric acid.
Precisely. And this difference in behavior is directly linked to the electronegativity difference between the element and oxygen.
Right.
Metallic elements have lower electronegativities than oxygen, so they tend to form ionic bonds with oxygen, resulting in basic oxides.
Okay.
Non-metallic elements, on the other hand, have electronegativities closer to that of oxygen, leading to covalent bonds and acidic oxides.
So it's like the tug-of-war for electrons again. The bigger the difference in electronegativity, the more likely the bond is to be ionic and the oxide to be basic.
Exactly. And this concept extends beyond just simple acidic and basic oxides. Some oxides, like aluminum oxide, exhibit amphoteric behavior.
Amphoteric, that sounds familiar, but I can't quite recall what it means.
Amphoteric oxides can act as both acids and bases, depending on the conditions.
Oh,
They can react with both acids and bases, showcasing a remarkable chemical flexibility.
it's like they're the chemical equivalent of a switch hitter in baseball, able to play both sides of the field.
A very creative analogy.
Thanks.
And this amphoteric behavior is often observed in oxides of elements that lie on the borderline between metals and nonmetals.
So they're like the in-betweeners of the periodic table, not fully committed to being a metal or a non-metal.
Exactly. And this duality in behavior reflects the nuanced nature of chemical bonding and the interplay of various factors like electronegativity and atomic structure.
It's fascinating how these, seemingly simple concepts, oxides, acids, bases, reveal the complexity and interconnectedness of chemistry.
Indeed. And as we delve further into the world of chemical reactions, it's crucial to remember that electron transfer is at the heart of many processes.
Right. Whether it's an alkali metal giving up an electron to a halogen or a nonmetal oxide accepting electrons from water, these electron transfers drive chemical transformations.
And to keep track of these electron transfers and understand the changes in an element's oxidation state during a reaction,
Yeah.
we use those handy bookkeeping tools we discussed earlier, oxidation numbers.
Oxidation numbers, those little superscripts that tell us if an element has gained or lost electrons. They're especially important when dealing with those versatile transition metals.
Absolutely. Transition metals, with their ability to exhibit multiple oxidation states, can participate in a wide variety of reactions. And to clearly indicate which oxidation state a transition metal is in, we use Roman numerals in the compound's name.
It's like giving each transition metal a unique code based on its electron configuration.
Yes.
For example, iron can exist as iron 2 with an oxidation state of +2.
Yes.
Or as iron 3 with an oxidation state of +3.
Precisely.
And this distinction is crucial because iron 2 and iron 3 compounds exhibit different properties and reactivity. For instance, iron 2 oxide, also known as ferrous oxide, is a black powder commonly used as a pigment.
Right.
While iron 3 oxide, also called ferric oxide or rust, is a reddish-brown compound.
Exactly.
It's amazing how a simple change in oxidation state can lead to such distinct differences in a compound's properties.
It is. It's a testament to the power of electrons and their role in shaping the chemical world.
I'm eager to learn more, but that feels like a great place to pause for now.
Okay.
We've covered a lot of ground, from balancing equations to the intricacies of the periodic table and oxidation states. It's incredible how these seemingly separate ideas are all interconnected, each building upon the other to create a coherent picture of the chemical world. All right, so we've laid a solid foundation, but those alkali metals and their explosive reactions with water are still on my mind. Why are they so much more reactive as you move down the group?
Well, that explosive reactivity is all thanks to ionization energy. As you descend group 1 on the periodic table, the outermost electron is further from the nucleus and experiences more shielding from inner electron shells.
So that outermost electron is held less tightly.
Exactly. It's easier to remove, making those elements eager to react and form positive ions. And this reactivity trend isn't limited to water. It also applies to their reactions with halogens.
Right, the alkali metals and halogens have that classic attraction, forming salts in the process.
Yes, think of it as a perfect partnership. The alkali metal, with its lone valence electron, is happy to donate it to the halogen, which needs just one more electron to complete its octet.
So they both achieve stability through this electron exchange.
Precisely. This transfer of electrons forms an ionic bond, creating a salt, a compound composed of oppositely charged ions.
And that's a pretty fundamental reaction with applications everywhere, from table salt to industrial chemicals.
It is.
Now, the source material also mentioned halogen displacement reactions. What are those all about?
Halogen displacement reactions are a kind of chemical competition. Imagine adding chlorine to a solution of potassium bromide. The chlorine, being more reactive, will displace the bromine, forming potassium chloride and leaving bromine behind.
So it's a battle for that coveted electron. The more reactive halogen wins.
A very apt analogy. And remember, halogen reactivity decreases as we go down group 17.
Right.
Fluorine is the most reactive, followed by chlorine, then bromine, and lastly, iodine. This hierarchy dictates the outcome of these displacement reactions.
It's fascinating how predictable these reactions are, all thanks to the periodic table. Now, I'm still a bit hazy on acidic and basic oxides. These seem straightforward, but I need a refresher.
Well, oxides, compounds formed by an element reacting with oxygen, can indeed be acidic or basic.
Right.
It all depends on the character of the element.
So metallic oxides are generally basic.
Correct. Think of group 1 and 2 metals.
Oh, okay.
Their oxides react with water to form alkaline solutions. Sodium oxide, for instance, produces sodium hydroxide, a strong base.
Okay, and non-metallic oxides are acidic.
Precisely. Take sulfur trioxide.
Okay.
When it reacts with water, it forms sulfuric acid. This difference in behavior comes down to electronegativity.
Okay, so it's the electronegativity difference between the element and oxygen that matter.
Exactly. Metallic elements with lower electronegativities than oxygen tend to form ionic bonds with oxygen, resulting in basic oxides.
Got it.
Non-metallic elements with electronegativities closer to oxygens form covalent bonds and thus acidic oxides.
It's amazing how much those tiny electrons influence the properties of entire compounds.
Oh.
The source also mentions amphoteric oxides, which always sounded like a tricky concept.
Amphoteric oxides are the chameleons of the oxide world. They can act as both acids and bases depending on the environment they're in.
Oh, right.
Think of aluminum oxide. It can react with both acids and bases, showcasing a remarkable duality.
So it's like a chemical switch hitter.
Exactly. This behavior is often found in oxides of elements on the borderline between metals and nonmetals.
They can't seem to decide which side they're on.
And that's what makes chemistry so fascinating, this interplay of factors like electronegativity and atomic structure. But remember, amidst all this complexity, electron transfer is the driving force behind many reactions.
Right, those electrons are always on the move, whether it's an alkali metal giving up an electron or a nonmetal oxide accepting one.
And to keep track of these electron transfers, we use those handy oxidation numbers we talked about earlier, especially important when dealing with transition metals.
Because transition metals can have multiple oxidation states, right?
Absolutely. Transition metals add a layer of complexity with their partially filled orbitals, allowing them to exhibit a variety of oxidation states.
So to be clear about which oxidation state a transition metal is in, we use Roman numerals in its name.
Exactly. For example, iron can exist as iron 2 with an oxidation state of +2 or as iron 3 with an oxidation state of +3. This distinction is critical as different oxidation states lead to different properties.
So iron 2 oxide and iron 3 oxide, even though they both contain iron and oxygen, behave differently.
Absolutely. Iron 2 oxide is a black powder often used as a pigment, while iron 3 oxide is the reddish-brown compound we know as rust. A simple change in oxidation state leads to drastically different properties.
It's incredible how those tiny electrons have such a profound impact on the chemical world. I'm definitely ready to learn more about those versatile transition metals. All right, let's dive into those fascinating transition metals. They seem to be the rule breakers of the periodic table, exhibiting multiple oxidation states. What makes them so unique?
Well, transition metals owe their unique properties to those partially filled d orbitals we touched upon earlier. Unlike the s and p orbitals, which tend to fill up completely, those d orbitals can accommodate different numbers of electrons, giving rise to a variety of oxidation states.
So while alkali metals and halogens stick to one oxidation state, transition metals like to keep things interesting. Is that why they form such colorful compounds?
Exactly. The presence of d electrons leads to a phenomenon called dd transitions, where electrons can absorb and emit light in the visible spectrum, resulting in those vibrant colors we associate with a transition metal compounds.
I always thought it was interesting how solutions containing transition metals could change color depending on what was added.
Yeah.
Is that related to these D and D transitions?
Absolutely. The environment around a transition metal ion can influence the energy levels of its d orbitals, altering the wavelengths of light it absorbs and emits. This means the color of a transition metal complex can change with factors like pH, concentration, or the presence of other ligands.
So it's like the transition metal ion is responding to its surroundings by changing its color.
That's a great way to visualize it. And this sensitivity to the environment makes transition metals incredibly versatile, allowing them to participate in a wide array of chemical reactions and form diverse compounds with unique properties.
Okay, so we know transition metals can have multiple oxidation states. How do we determine which oxidation state a transition metal is in within a specific compound? It seems like it could get a bit tricky with all those possibilities.
It does require some detective work, but there are some helpful guidelines. We need to remember that the sum of the oxidation states of all the atoms in a neutral compound must equal 0.
So it's like a balancing act again, just like with those chemical equations we discussed earlier.
Precisely. And we can often use the known oxidation states of other elements in the compound to deduce the oxidation state of the transition metal. Oxygen, for example, usually has an oxidation state of 9-2, except in peroxides.
So if we have a compound like iron oxide, Knowing oxygen's oxidation state can help us figure out iron's oxidation state.
Exactly. Let's say we have the compound F2O3. To have an overall neutral charge, the two iron atoms must have a combined oxidation state of +6 to balance the 9 from the 3 oxygen atoms.
So each iron atom in Fe2O3 must have an oxidation state of +3. That's why it's called iron 3 oxide.
You got it. It's all about using the clues we have to solve the oxidation state puzzle.
This deep dive has really highlighted the complexity and interconnectedness of chemistry. We started with balancing equations, delved into the intricacies of the periodic table and electron configurations, and now we've explored the captivating realm of transition metals and their multifaceted behavior.
And we've only scratched the surface. Chemistry is a vast and ever-evolving field, constantly pushing the boundaries of our understanding of the universe and the intricate dance of matter and energy.
It's amazing how these seemingly separate ideas are woven together, revealing the elegance and beauty of the chemical world.
It is.
I'm leaving this deep dive with a newfound appreciation for the wonders of chemistry.
And remember, chemistry isn't just confined to textbooks and laboratories. It's all around us, shaping our world in countless ways, from the air we breathe to the materials that make up our everyday lives.
So to all you curious minds out there, keep exploring, keep asking questions, and keep unraveling the mysteries of the chemical world. Who knows what amazing discoveries await?